I need to do a change in the schedule here. Tomorrow's lab I have scheduled for experiment 10. I'm going to switch these two. So we'll do experiment 8 tomorrow, which is a dry lab, and then experiment 10 on November 8th.
Oh, is 8 the one where we put the stuff together?
No. Not, well, yeah, actually it is. Molecular geometry. We're going to do this in 2 parts. First, we're going to draw out what are called the Lewis structures, and then we'll do the geometries of the shapes of those things.
I have a question.
Uh-huh.
What about the labs that we haven't turned in?
Okay, experiments, the chemical reactions experiment.
Yeah, you said you wanted to talk more about that before we had it in.
Well, this is what I want for those. For the chemical reactions labs, we did double replacement and single replacement reactions.
Yeah.
And so what I want to do is I want you to write the CE, the IE, and the NIE for all the reactions, for all reactions. Not the ones that you didn't do, for all reactions done.
You know the first part is didn't actually ask for a reaction to rate it? And those ones too?
No, just the ones that you mix the chemicals together in the test tubes. This one is the ones that are done for single replacement and double replacement. Now, you did a couple of others that you could just write the CE for. Dehydration and decomposition of the dehydration was the copper sulfate pentahydrate solid. The decomposition was the copper 2 carbonate solid.
Do you want us to label the states as well?
Yeah. Except aqueous you can leave on. I don't have to write that for aqueous. So I just want, you can write this on a separate sheet of paper or something, just all the equations for the reactions. That's what I want for that. And that plus your observations, that's enough. So you don't have to fill out the report sheet for those. All right, any other questions?
So will that be due tomorrow? Or can it be for next week?
No, you can turn it in next week. Just finish it. So for experiment 8, you don't have to do any prep for that. And so again, moving experiment 10, we're going to postpone it to November 8th. We'll do experiment 8 tomorrow. Right now we're still dealing with chapter 11, but chapter 11, 12, and 13 are all related. And so we're going to discuss some of the chapter 11 stuff, along with 12 right now. So we left off with what element? Germanium? Is that right?
Yeah.
Germanium is argon, 4s2, 3d10, 4p2. And so if we look at the electron configuration, it's going to be argon, 4s2, 3d10, 4p2, or argon, 3d10. These would be called the inner or the core electrons, followed by 4s2, 4p2. These would be the valence electrons. This is valence. These are inner or core electrons. Now, when I look at this, argon, I mean, in order to fill the fourth shell, we would need how many more for germanium? We would need 4 more electrons. So 1, 2, 3, 4. If we had 4 more electrons, we could get 4s2, 4p6. And so germanium can actually gain, let's say gain plus 4 electrons. We fill the fourth shell. Versus gallium would be hard because how many electrons would gallium have to gain to fill the fourth shell? It'd have to gain 5 electrons. Gaining 5 electrons is going to be difficult. In fact, gaining 4 electrons is very difficult. So this is not likely to happen. What's more likely to happen is germanium will lose 2 or lose 2, that's the 4p, or lose 4. So plus 2 plus 4 would be okay for germanium. What about tin? What do you think tin is? Plus 2 plus 4. Lead? Plus 2 plus 4. Do you see? All of them are going to just be offset. So if this is germanium, tin would be 5s2, 5p2. And so plus 2 plus 4. Lead would be 6s2, 6p2. So plus 2 plus 4. And so we could lose 2 electrons or we could lose 4 electrons. And that will take care of what we call the valence electrons.
What does that say? Inner, outer, core?
Inner or core versus valence. Germanium. After germanium comes arsenic. If we look at arsenic, it's 4s2, 3d10, 4p3. So the 2 electron configurations we'd write are argon 4s2, 3d10, 4p3, or argon 3d10, that would be the core or the inner, and then the outer would be 4s2, 4p3. So arsenic can do different things. If we were to fill the shell, the fourth shell, how many more electrons are required? 3. So arsenic can gain 3 electrons, fill the fourth shell. Or it could lose how many? It could lose 3 electrons. That would give us arsenic 3. Or it could lose 5 electrons. That would give us arsenic 5. 3 and 5 are the common. So arsenic is plus 3 plus 5. What about antimony? You'd expect antimony to be plus 3 plus 5 and bismuth plus 3 plus 5. Or the other option is minus 3. Just like if you look at phosphorus, where are we? Phosphorus would be plus 3 plus 5 or minus 3. Does that make sense? They're all in the same family, so they all have a similar kind of electron configuration, just offset by 1. If we go to selenium, selenium is going to be argon 4s2, 3d10, 4p4. actually 4p4 looks like that. So when we look at selenium, selenium is going to be argon 4s2, 3d10, 4p4, or argon 3d10, 4s2, 4p4. So when we think about selenium, probably the easiest is just to fill this shell. If we fill this shell, how many more electrons does it want? 2. So if it gains 2 electrons, then it fills the cell. So we'll get selenide. That would be filled. If it loses electrons, then we can go maybe +4 or +6. So +4 and +6 are common for selenium if we lose, or -2 would be common. And so we lose -4 electrons. Losing 4 electrons is getting difficult. Losing 6 electrons is difficult as well, etc. Does this make sense? Someone? All right. And so the pattern continues. So basically, the theory, the observations, the periodic table came from observations. And what's the theory that underlies the periodic table? What's the name of the theory that describes the periodic table in a more fundamental theoretical way? When the periodic table was first developed, all the elements were grouped into families, and these families had similar properties, and then you had these rows or periods, and the properties varied smoothly across the period. But that was all from observation. But when we look at the orbitals and quantum mechanics is the theory that underlies the periodic table. And then we see quantum mechanically what's going on. So let's take a look at the book, and then take a look at the dealing with here. So here we can see the orbitals, and so this is a more fundamental description of the periodic table, and this is theory. Here you see another thing. What is this? This is the energy level diagram, but it's really written more as an orbital box diagram. Do you see that? It doesn't really show the spacings on this. Like, for example, there's a big gap between 1s and 2s, but there should be a tiny gap between 2s and 2p, or a much smaller gap, not tiny. And so this isn't very good. So figure 11-21, don't bother learning that. It's not worth. This you should know. It's everyday chemistry. Skip that. Atoms. Skip that. Electron configuration. So we just did our electron configuration. We didn't complete this all the way across, but you can see. The other pattern that we see is that all of the members of the family will have the same valence electron configuration. And so if I look at this as 1s1, 2s1, 3s1, 4s1, the core will change, but the valence stays the same. So all members of this family have one valence electron in the highest shell, 2 valence electrons, etc. If we go back to when we're looking at over here, like for example with arsenic, nitrogen has 3 valence electrons. It goes 1s2, 2s2, 2p3. Phosphorus has 3 valence or five valence electrons, 2s2, 2p3, phosphorus, 3s2, 3p3, arsenic, 4s2, 4p3. These 3d10 get rolled into the inner. So they all have the same number of valence electrons. So what we're going to do here is we're going to represent these by Lewis symbols. So sodium has one valence electron, because when we look at sodium, what's the electron configuration for sodium? It's going to be neon 3s1. So neon 3s1. So here's our one valence electron. We show that by a dot. And then magnesium is going to have two valence electrons, which we show by dots like this or X's. This will be neon 3s2. And then we go across the board. Aluminum comes next. If we go to aluminum, that has three valence electrons. Now, we have four regions of space. So magnesium, we usually pair them up like this. But aluminum, we'll write them separate like that. And so this will be neon 3s2, 3p1. So that's a total of three valence electrons. Each of those, so two of these dots will be the S, and one of the dots will be the P. But if you're an oxidizer, you can take all three without too much difficulty. And then from aluminum, we go to silicon. Silicon will have four dots in these four regions of space like this. So we write them separately. And that's going to be neon 3s2, 3p2. So it's four valence electrons. Those four dots. And then phosphorus, we have to do one pair like that, in these four regions of space. So we'll have one pair, and this will be neon 3s2, 3p3. Now, this pair doesn't necessarily mean they're paired in the orbital like that. Like, for example, these 2s electron, these two 3s electrons will be paired. These will be single, but I'm writing all four singles, no paired, even though this is going to be paired. And so there isn't a correlation between these. Technically, I have two that are paired, one that's unpaired, but I draw these three single. Okay, then I have phosphorus and then sulfur. Sulfur has six, and so I draw them like this. Two singles, two paired. But when I look at the electron configuration, it's going to be neon 3s2, 3p4. 3p4 gives us three paired in the electron configuration. If I looked at this in terms of the orbital box, I'm going to have a box for the 3s, and those are going to be paired. And then I'll have three boxes for the 3p. And I got four electrons, tons of roll, and then here I only see, actually this one worked out, two paired and two singles, but it's not necessarily correlated. It just so happens to be here. Whereas in phosphorus, it was correlated. In silicon, it wasn't. In silicon, we have neon here, and we'll have the 2s, I mean, not the 2s, the two 3s electrons, which are paired, plus the two 3p electrons, which would be unpaired. And so here I have one paired, two unpaired, or two singles. And when I draw the Lewis symbol, these are called Lewis symbols. We draw three singles. Sulfur and then selenium. I'll draw 3 pairs and 2 singles. Not selenium, I'm not doing selenium. After sulfur comes what? Chlorine. Chlorine, I'll draw 3 pairs and 1 single. And then finally, argon, which will have 4 pairs. And so chlorine is going to be neon, 3s2, 3p5. So that's just 1 electron short of filling. And then argon is going to have filled. So it's going to be neon, 3s2, 3p6. Neon 3s2, 3p6 is equal to argon, the core. So the third shell's filled.
Is there a way we should put it?
You should put it argon. This is the preferred method. So argon's why we have an octet. To fill the valence orbitals is going to require an octet, 8 electrons, 2 for the S, 6 for the P. The octet is going to lead to stability. Once we fill that shell, but we don't want to break out that shell. So a full shell filled is quite stable. A subshell filled is really stable, but not as stable as a full shell. All right. This is the periodic table. If we're doing electron configurations, the easiest thing to do for electron configurations is just use the periodic table to figure them out. I'm not going to do any complicated ones, so ignore some of those. The second half of chapter 11 deals with something called periodic trend, periodic properties. The first periodic trend is the biggest atom. Where's the biggest atom? Bottom left, cesium. Where's the smallest atom? Top right, helium. And so this is the trend you should know. The smallest is up here, and the biggest is down here. And so the atoms decrease in size. And so as we go right, the size decreases, and as we go up, the size decreases. As we go left, the size increases. As we go down, the size increases. So,
Is helium really small than hydrogen?
helium is smaller than hydrogen, but when you look at these, it doesn't look like it, does it? This is the radius here. 37 picometers. So you have 37 picometer radius here, and helium is a 31 picometer radius. And so 6 picometers smaller. But they screwed up this graphic. Whoever made it screwed it up. Helium should be smaller. Why is helium smaller? It's got more stuff. And so the reason helium is smaller is like this. Hydrogen has only 1 proton and 1 electron in the 1s orbital. This would be hydrogen. Helium has 2 protons, and it has 2 electrons in the 1s orbital. And so what happens is with 2 protons, the electrons get pulled in closer. It's like, science fiction tractor beam or something like that. This electrical force is pulling the electrons closer. As it pulls in the electrons closer, they can't get as far away. And so for hydrogen, it's a weaker electrical attraction. For helium, it's a stronger one, which makes it smaller. So helium is smaller than hydrogen because of electrical forces. Does that make sense?
Yeah, and that's why as you move to the right, on the same level, it decreases in size.
Yeah. So as we move across here, we have greater nuclear charge. So we have an increase in nuclear charge. But lithium has 3 protons. Helium has 2 protons. So lithium you predict to be even smaller. But the problem is we're going to fill the next shell. And the next shell has orbitals that are going to be 4 times bigger. And therefore, the reason the size, it's successive shells. So the first shell, second shell, third shell, just gets bigger and bigger and bigger. And so here, as we go up, the size decreases because fewer shells. The size increases in the opposite direction because we have more shells. Does that make sense for the size trend? I don't know if you have to know that. In Chem 1A, we spend a lot of time talking about that. This is a size trend. We have something called ionization energy. If you're an oxidizer, is it easier to take this electron or is it easier to take this electron? That one. And that's ionization. Ionization is stripping the electron off. The first one is size. Next one is ionization energy. How much energy does it cost to strip an electron off an atom or an ion? Increasing ionization energy. The smaller the atom is, the harder it is to ionize. The bigger, cesium would be the easiest to ionize. It's big. Electrons in a shell that's pretty far away from the nucleus. Helium would be tough to ionize. It's small. And so the smaller the atom is, the harder it is to ionize, therefore it's going to cost you more energy. So it follows the size trends. Smaller, more difficult, more energy. Bigger the atom is, the easier it is to ionize. And so ionization energy follows the size trend. The smaller it is, the harder. The bigger it is, the easier.
So helium has the greatest ionization.
Yeah. Helium has the highest ionization energy on the periodic table. Helium is going to be the most difficult element to ionize. It's so difficult to ionize helium that they call helium an inert gas. It doesn't want to react with anything. If an oxidizer comes along, it's going to have a very tough time trying to oxidize helium. Same thing with neon. Argon, maybe. Xenon and krypton, yes. Oxidizers can come along.
Is that nuclear charge or nuclear change?
Nuclear charge. Z. Nuclear charge is how the positive charge in the nucleus. So sodium's fairly easy to ionize. It's got this one electron here. The first electron's easy to ionize. And so we can form sodium plus. But in order to ionize the second electron off sodium to form sodium 2 plus, you'd have to strip a core. That is, this is helium neon. You have to break up the neon core. That is the shell, the filled shell. And so it's going to stop here. because it's too hard to break this apart, too hard to ionize that. And so that's where we stop. I'm wrong now. So helium has the highest ionization energy, hydrogen lower. Lithium's a lot lower. It drops here because that's the next shell. The next shell it's easier to strip. But what happens with lithium is you go from lithium to beryllium. Beryllium's smaller. And then you go to boron. And so there are little blips here. And you don't have to have this memorized, but let me tell you what causes the little blip. If we strip off lithium, that's a 2s. If we strip off beryllium, it's a 2s. But when we get to boron, it's 2p. So it's a little bit easier to knock a 2p electron off than a 2s. So that's why there's a little dip here. And then we go to carbon, that's another 2p. We go to nitrogen. And then there's a little blip here for oxygen. Oxygen's easier to ionize than nitrogen. The reason oxygen's easier is because of a paired electron. And so the two blips are caused by this. And again, I don't think you're going to have to worry about this. So for beryllium, we're knocking this electron off. For boron, we're knocking this one off. This is a 2p. That's it. For nitrogen, which is going to have 2s2, 2p, 3. So for nitrogen, we're knocking this one off. But for oxygen, which is going to have 2s2, 2p4. For oxygen, it's going to be a little bit easier because we're removing a paired electron versus unpaired. A paired electron is going to have electron-electron repulsion. Making it a little bit easier. But once we get to fluorine, then it doesn't matter. It's also paired. And so the size decreases. So lithium's bigger, beryllium's smaller, boron's smaller than beryllium. But boron's even smaller, but it's a 3p we're knocking off. And then nitrogen's smaller, and then we go to oxygen. Oxygen's even smaller, but we're knocking off a paired electron. Otherwise, it follows a size trend. So the smaller the atom, the harder it is to ionize. Helium, neon, argon, krypton, these are all very difficult to ionize. Yeah. Lithium, sodium, aluminum, potassium, cesium, rubidium, cesium, these are all very easy to ionize. So ionization energies vary this way. We'll talk more about these, but this is just the general trends in that. And then we have families that all have the same valence electron configuration. And so some lose electrons more easily, some gain electrons more easily. We've been talking about that already. Some of the more complicated electron configurations, these are weird. Like for example, hafnium. Hafnium, you would go xenon, and then this is 1, 2, 3, 4, 5, 6. 6s2, and then 3d, 4d, 5d. 6s2, 5d1, and then you drop down into the lanthanides. And so we follow the periodic table when we're doing more complex electron configurations, but I don't think I'm going to give you any. But some of them are kind of tricky because they're more exceptions. Let's see if I can grab So when we do electron configurations of the periodic table, let me show you what we do. Yeah. Let's say I want the electron configuration for tungsten, which is W here. How would I do that? Well, tungsten's element number 74. So what I'd do is I'd work backwards until I get to the core, noble gas core before 74. So I can't go to radon, which is 86. I'd have to go to 54, which is xenon. So if I'm looking for the electron configuration for tungsten, I'd start off with xenon with 54 electrons. So let's do this. So let's start off with xenon. That has 54. Now where does the 55th electron go? Tungsten has 74 electrons. So this is 54 electrons. This is 74 electrons. So where does electron number 55 go? Electron number 55 is here at cesium. And so this is 1, 2, 3, 4, 5, 6. 6s. So 55, 56 would be 6s1, 6s2. 6s2. Now, I can figure out how this feeds, but the periodic table is going to tell us how it goes. Do you see where 57 is? 57 is, okay, if this is 6s, this would be 3d, 4d, 5d. And so 57 is 5d1. This is really weird. So 67 is 5d1. And then I have to go to 58. 58 is down here. Do you see that? And so it would go, this would be 4f, this is 5f. So it would go 4f all the way to 71. That fills 14. So we go 4f14. So if I'm interested in electron configuration for lutetium, element number 71, that would be it. It's weird. Lutetium would be xenon 6s2, 5d1, 4f14. But I'm going to continue because I'm going to element number 74. So I go from 71 to 72. Well, if I'm at 72, I'm back in 5d. So 72, 73, 74 would be another D, and another D. 3 more D electrons. And so this would be 5d3. But we're not going to separate it. This is how it fills. And so what we're going to do is we're going to combine it. When we combine it all, we're going to get xenon, 6s2, 5d4, 4f14. Or xenon, and then we do it in numerical order. 4f14, 5d4, 6s2. So we could use the periodic table to do it, but I'm probably not going to give you, any weird ones like this. Just do the more straightforward one. But that's how you do it if you're given something like that. All right. What I want to do now is jump to chapter 12. Yeah. Because this is chemical bonding part 1, 12 and 13. So here we can see this is the element phosphorus. There are 2 different forms. Phosphorus can form these cage molecules, this is P4, or it can form these long chains. This is red phosphorus here, this is white phosphorus here. They have totally different colors. They also have totally different properties based on their structure. Like P4 is unstable in air, it's stable underwater, so it's usually stored underwater. You don't want to expose it to oxygen. Red phosphorus is fine, it's stable in air. And so the properties are different because the structure is different. The structure is different because of how they bond together and what types of structures they form here. So let's spend some time looking at these. You guys already know this, correct? The charges. And the charges are just filling the shell or losing electrons to get the core. What we want is we want a core that is a noble gas core electron configuration. And sometimes we have a modified core where the 3D or the 4D participate in the core. This is what's happening with electron configuration. So we're looking at nitrogen. Nitrogen can gain 3 and fill that shell. Oxygen can gain 2, chlorine can gain 1, neon doesn't want to do anything. But here, sodium would have to gain way too many. Sodium would have to gain 7 electrons to fill the shell, the third shell. This is too far away, so sodium loses. So the things on the left tend to lose, the things on the right tend to gain. And so if sodium loses, then we're left with the neon core here, etc. And so we're going to take a look at Lewis structures now. So if I have sodium, which has 1 valence electron, reacting with chlorine, chlorine has a total of 7 valence electrons. Chlorine is just 1 short of filling that shell. It needs 8 valence electrons to fill that shell. So chlorine is going to come over and take the electron from sodium. Sodium has a relatively low ionization energy compared to chlorine. And so it's not too difficult to ionize sodium. And then what we end up with is sodium with no valence electrons. We show that like this. There are no dots around it. And it's going to have a positive charge because we lost 1 negative charge. And then chlorine with a filled valence shell. The filled valence shell is called an octet. So we'll have an octet. The chlorine would be 3s. 2, 3p6 would be filled. That would be it. Sodium is going to be, what is sodium? Neon. 3s.
Do we add the brackets when it's an ion?
Yes. We add the brackets when it's an ion. And chlorine is going to be neon. 3s2, 3p5. Sodium plus is just going to be neon, so that's stable. And then chlorine will be neon. 3s2, 3p6, which is equal to argon. And so we have the noble gas configuration. This is called a formula unit, and then what we have is we have a lattice of sodium ions and chloride ions. And so this is a formula unit. And then the lattice we can represent as a Lewis structure as well. When we do the lattice, we have the sodium bracket with positive on the outside, chlorine with an octet with 8 dots with a negative, followed by sodium, followed by chlorine with an octet or chloride. And then for each sodium, we want as many chlorides around that as possible. And for each chloride, we want as many sodiums around that as possible. So this would be the lattice. And so this is the Lewis structure for a formula unit, and this would be the Lewis structure for the lattice for sodium chloride, or the crystal. We can build up the lattice here. So here we show the ions. The sodium ions are the gray, the chloride ions are the green here. And this would be the lattice. And here's a picture of the salt crystal there. Here's trying to show the cloud. Cumulatively, the cloud is kind of spherical. See? What's happening with the size, though, is kind of interesting. As we go across from sodium to chlorine, it gets smaller. You know, the number of protons increases. And so sodium is bigger than chlorine. But when sodium loses an electron, it shrinks to about half the size. And when chlorine gains an electron, it doubles in size. So chlorine ends up being bigger than sodium ions. Whereas when we're looking at it in the periodic table, the size decreases as we go left to right. Something funny happens with the size. You don't have to memorize that. And so this would be the lattice here. There are different lattices. This is calcium carbonate here. The carbonates have a different shape. So the lattice looks a little bit different here, calcium carbonate. Let me show you what that looks like. We have some lattices, we have some orbitals. I'll bring them in. Okay, but chlorine would like to have that, what we call the octet. And so chlorine has no problem taking an electron from sodium, but what if it tried to take it from another chlorine? The chlorine has 7, it's just 1 electron short. This chlorine has 7, it's 1 electron short. So what's going to happen are the 2 chlorines are going to try to take each other's electron. And so this chlorine is going to try to pull off this electron, this chlorine is going to try to pull off this electron. Well, what's going to result in is a tie. When we have a tie, we end up doing this. We end up sharing that pair of electrons. And so we end up double counting this. So for example, this chlorine will now have an octet, but this pair doesn't really belong all to this chlorine. And this chlorine ends up having an octet in a shared manner like this. And so we gain an octet here and an octet here by sharing. Electrons. Okay, so to represent that sharing arrangement, we draw this. The line represents what we call a covalent bond. That would be the shared pair. So this is a covalent bond here. And we just convert that 2 set of dots into a line. Over here, we have something called an ionic bond. The ionic bond is not shown with the line. It's just shown with the ions adjacent to one another. So this is an ionic bond here. And so 2 different kinds of bonding. Here, the chlorine didn't have to share. The chlorine could just take the electron. Over here, the chlorine couldn't take the electron. It has to share. And so it depends on how strong each of these species are.
Are all ionic bonds lattice?
Yes. They're all lattice. Hydrogen is 1 electron short from helium of filling its shell. So hydrogen can fill the shell by sharing here. So if it shares it, then we end up with something like this. Now, a covalent bond is actually electrical in nature. So let's take a look. On ionic bond, we see electrical attractions hold the atoms together. The covalent bond also has electrical attractions, but it's a little more difficult to see. How that results. And so it's probably easier to see in the case of hydrogen. So let's take a look at hydrogen, which is a bit simpler. Hydrogen has 1 valence electron, so it could either gain or lose 1. But in this case, let's say these 2 hydrogens want to gain, so they're going to try to take each other's electrons, which is going to result in a sharing scenario like this, which we write like this. Now, when we look at a hydrogen atom, we have the proton, and then we have an electron cloud. And this electron cloud would be a 1s electron here, in that. And then over here, for this hydrogen, we have a proton and an electron cloud here. Yes. So when they end up bonding to one another, what we get is we get these overlapping electron clouds here. In the overlap region, we're going to have a higher density of dots than in the other regions. That's what they're trying to show over there. Higher density. A higher density means more negative charge in this region. So we got more negative charge in this region here. A buildup, and less negative charge out here. So what we have is we have the electrical attractions between the protons and this more negative charge region here. And since we have the overlapping dots, they're going to just double up. So that's what they're trying to show here. They're trying to show us there's going to be increased density, electron cloud density here in this region, which means higher probability of finding electrons in between the two nuclei. We want the electrons in between the two nuclei because that's what's going to hold them together. If the electrons are not there, then the two nuclei see each other and they're going to be repelled. That is positive repels positive, and that will break the bond. So we need the electrons to be more focused in here in this region than out here in that region. And so that's what holds the covalent bond together. Now, we have some scenarios here. So if we have sodium and chlorine react, this forms an ionic bond. Like that. If we have chlorine and chlorine react, this forms a covalent bond. So this is ionic, this is covalent. Ionic is chlorine is going to take the electron, so there's going to be a winner and a loser. Covalent, they just share, even sharing. But what if we have something like hydrogen and chlorine react? Is hydrogen strong enough to take the electron? I mean, not hydrogen. Is chlorine strong enough to take the electron from hydrogen? Well, hydrogen, the ionization energy is a lot higher than sodium. It's a smaller atom. And so it's more difficult to ionize than sodium. Sodium is really easy to ionize. Hydrogen's a lot harder. And so what happens is chlorine's not strong enough. So if chlorine's not strong enough, they end up sharing. But they don't share evenly. So for example, if I look at this chlorine here, this cloud is represented by this pair is completely on the chlorine. If I look at this chlorine, this cloud here represented by this pair is evenly distributed between the two chlorines. However, if I look at this one, this hydrogen doesn't let go completely. Chlorine's stronger, and so it pulls more of the cloud towards itself, but it can't completely pull it like here. Here it's completely pulled it off, here it hasn't. And so we end up with this scenario. This scenario is between covalent and ionic. Between covalent and ionic, we call it polar covalent. Polar covalent, we're going to have an asymmetric electron cloud. In purely covalent, we have the symmetrical electron cloud. In ionic, it's completely lopsided. It's totally asymmetric there. And so that's what they're talking about, polar and non-polar covalent bonds. Non-polar covalent bonds are even. So this would be an example of a non-polar covalent bond. It's evenly shared. An ionic bond is totally uneven. One side wins, the other side loses. A polar covalent bond is in between a covalent bond and an ionic bond, so it's somewhere in the middle region here. And it just depends on how hard it is to ionize X in this case, or M. So what we're going to spend most of our time doing, well, how hard it is to ionize, well, it depends on something called electronegativity. There's a tug of war for electrons. And the strength is going to be given by the electronegativity table. Fluorine is the strongest. It gets 4.0. Cesium and francium is the weakest. Francium is the weakest here. It gets a 0.7. And so what we do is we look at the electronegativity. How big of a difference is there here in the electronegativity? So in this case, let's take a look at chlorine. Chlorine is a 3.2. Sodium is a 0.9. And so 3.2 versus 0.9. Well, 3.2 is going to win. And when we look at the delta EN here, these are the ENs. The delta EN is going to be 2.3. 2.3 is what we call ionic. There's going to be a large difference in their strength. Versus here, chlorine versus chlorine. This is a 3.2. This is a 3.2. So delta EN here is going to be 0. There's no difference. We're going to end up with a tie. Over here, we have a 3.2 on chlorine, and hydrogen is a 2.2. So delta EN is not as big. Delta EN here is just 1.0. And that's what we call polar covalent. So what we have, we're going to have some cutoffs here. If the difference in strength is significant, it's going to result in an ionic bond. And so ionic bonds are going to be characterized by having a delta EN greater than about 2. This is not set in stone here. And so these numbers are just rough, approximate cutoffs. Polar covalent ranges from a delta EN of about 0.6 to about 2. And what we call non-polar covalent is going to be from 0 to about 0.5 with a delta EN. And so it's fairly evenly mapped. So let's look at the HO bond here. H is 2.2, O is 3.4, so our delta EN is 1.2. An HO bond should be 1.2 makes it what? Polar covalent. An HS bond, 2.6 versus 2.2. It gives a 0.4. So HS bond is nonpolar covalent. HP bond, 2.2 versus 2.2, nonpolar covalent. HC bond, nonpolar covalent. And so there's very little difference. Sometimes we end up with multiple bonds. Let's take a look at some multiple bonds here. Next. Oxygen has 6 valence electrons, so it wants 2. So if I have 2 oxygens come together, each one of these wants 2 electrons. So this oxygen is going to try to take the 2 electrons here, and this oxygen is going to try to take 2 electrons here. Well, what's their difference in electronegativity? 0. And therefore, well, it's going to have to result as a polar covalent bond. In this polar covalent bond, they're going to end up sharing 4 like this. So this oxygen ends up with an octet. This oxygen ends up with an octet. So we end up with an octet here and an octet here. But it means sharing 2 pairs of electrons, which is 4 electrons. And if that's the case, we end up forming what's called a double bond here. And so, again, we get the octet here. We have to double count these bonding electrons in the octet here. Delta EN 0, so this would be a nonpolar covalent bond. So oxygen will form a double bond. Nitrogen wants 3 electrons. Because nitrogen has 5 valence electrons. To complete the octet, it needs 3 more. And so what we end up with nitrogen is sharing 6 electrons. And so for nitrogen, we end up with a triple bond. The triple bond is strong, stronger than a double bond. Double bonds are stronger than single bonds. And so we just get more electrons jammed in the region. Okay. So we can form molecules like water. And so it doesn't have to take it from oxygen. We can take it from hydrogen and try that. So see what you form. Draw the loose symbols and see how you can add them up.